So this is the solution for question 7 of homework 7. In the question we are given a random process there of t which is equal to n1 of t cos omega ct plus theta plus n2 of t sin omega ct plus theta. Here n1 of t and n2 of t are White's stationary. Theta is uniform 0 to 2 pi and n1, n2 and theta are independent. So let's first denote the expected value of n1 of t as mu1 and expected value of n2 of t as mu2. So for a random process to be White and stationary, the mean or the expected value of the random process must be a constant, and the autocorrelation must be a function of tau, which is t2 minus t1. So it should only depend on the difference in time rather than the time. So first let's find the expected value of z of t. So expected value of z of t is expected value of n1 of t cos omega ct plus theta plus n2 of t sin omega ct plus theta. Since n1 and theta and n2 of theta are independent, we can separate the expectations. So since we have already denoted mean of n1 as mu1 and mean of n2 as mu2, we substitute that. And the expected value of cos omega ct plus theta is integral 0 to 2 pi cos omega ct plus theta and f theta of theta d theta. And expected value of sin omega ct plus theta is integral 0 to 2 pi sin omega ct plus theta f theta of theta d theta. So since theta is uniform in 0 to 2 pi, f theta of theta will be 1 by 2 pi for theta in 0 to 2 pi. Substituting that, so in integral of cos is sine and integral of sine is minus cos. Substituting the limits, we cancel out the sine terms here and the cos terms. So finally we get a zero mean. So here we have found out that the expected value of the random process is constant. Now let's find the autocorrelation function. So our z of t1 t2 is expected value of z of t1 multiplied with z of t2. So substituting z of t1 and z of t2 and multiplying the products, we get this expression. So we separate the expected value since it's a linear process, it's a linear operation. So we use this following three trigonometric identities. So here we have a cos A, cos B, sin A, cos B, cos A, sin B, sin A, sin B. So let's consider this as A, omega c t1 plus theta is A and omega c t2 plus theta is B. And using these identities, so cos omega c t1 plus theta times cos omega c t2 plus theta is 1 by 2 sin, this cos, so yeah, 1 by 2 cos omega c t1 plus t2 plus 2 theta plus cos omega c t2 minus t1, and theta cancels out over here. And similarly for sin omega c t1 plus theta cos omega c t2 plus theta, we use this identity. So we get 1 by 2 times sin omega c t1 plus t2 plus 2 theta plus sin omega c t2 minus t1, and theta cancels out. And similarly for this, cos omega c t1 plus theta and sin omega c t2 plus theta, we use the same identity, but we take a minus sign because we want it in terms of t2 minus t1. So we get a minus, so 1 by 2 sin omega c t1 plus t2 plus 2 theta minus sin omega c t2 minus t1. And finally for sin omega c t1 plus theta, sin omega c t2 plus theta, we use this identity. So we get 1 by 2 cos omega c t2 minus t1 minus cos omega c t1 plus t2 plus 2 theta. So using the basic trigonometric identities, we get the following expression. So and one more thing is we have to take the autocorrelation function of n1 as expected value of n1 of t1 times n1 of t2, which is, let's denote it as r n1 of t1 comma t2. Similarly for n2, the autocorrelation function is r n2 of t1 comma t2. So since we have these terms, the expected value of n1 of t1 and n1 of t2, which is the autocorrelation of n1, and expected value of n2 times n2 of t1 times n2 of t1, which is the autocorrelation of n2, and these will be mean of n2 times mean of n1, mean of n1 times mean of n2. So we substitute the identities and the autocorrelation, autocorrelation, how we denote it. So we get Rn1 of t1 t2 times the expected value of cos omega c t1 plus t2 plus 2 theta, which is integral 0 to 2 pi g of theta into f theta of theta d theta. This is a constant, so expected value will be the same, plus mu1 mu2 times 1 by 2 expected value of sine omega c t1 plus omega c into t1 plus t2 plus 2 theta. It's a constant again, so the expected value is the same. Similarly here mu1 mu2 times 1 by 2 integral 0 to 2 pi. So it is the expected value of sine omega c t1 plus t2 plus 2 theta, and the autocorrelation of n2 times 1 by 2 the minus expected value of cos omega c t1 plus t2 plus 2 theta plus cos omega c into t2 minus t1. So let us compute the integral separately. So this integral 0 to 2 pi cos omega c times t1 plus t2 plus 2 theta. So the integral of cos will be sine. So since this 2 theta divided by 2, substituting the limits 0 to 2 pi, we get sine omega c t1 plus t2 plus 4 pi minus sine omega c times t1 plus t2. So 4 pi plus theta will be, so 4 pi plus some phi will be phi. Therefore this will be sine phi minus sine phi. It will cancel out and we get a 0. Similarly for integral 0 to 2 pi sine omega c t1 plus t2 plus 2 theta. So integral of sine is minus cos. So this 2 theta, so we divided by 2, substituting the integrals from 0 to 2 pi. So let us take omega c times t1 plus t2 as phi. So we get cos phi plus 4 pi minus cos phi. So 4 pi plus phi is phi. Therefore we get a cos phi minus cos phi, which is a 0. Therefore the integrals in these two parts, these 4 parts, are 0. Substituting that, we get the autocorrelation of n1 rn1 of t1 comma t2 times 1 by 2 cos omega c times t2 minus t1 plus mu1 mu2 by 2 sine omega c t2 minus t1 minus mu2 mu1 by 2 sine omega c times t2 minus t1 plus the autocorrelation of n2 rn2 of t1 t2 by 2 cos omega c times t2 minus t1. So these two terms cancel out, and finally we get the autocorrelation of z as rz of t1 t2 equal to 1 by 2 times rn1 of t1 comma t2 plus rn2 of t1 comma t2 times omega c of t2 comma t2 minus t1. So the criteria for the random process to be twice and stationary is the mean should be constant and the autocorrelation must be a function of tau, where tau is t2 minus t1. So here, since n1 and n2 are already whites and stationary, rn1 of t1 t2 and rn2 of t1 t2 will be a function of tau, and we got omega c times t2 minus t1, where t2 minus t1 is denoted as tau. So we get cos omega c times tau by 2. So we finally get the autocorrelation is a function of tau. Therefore z of t is also whites and stationary. So rz of 0 is, substituting 0 in terms of in place of tau, we get cos 0 by 2 times r, the autocorrelation of rn1 of 0 plus rn2 of 0. So rn of 0 is simply the expected value of n1 square, and rn2 of 0 is simply the expected value of n2 square.